Hi guys, welcome to Engineering. Today I'm going to teach you the determination of height method. So this is the method you use trigonometric stations to determine your height of the point you are standing on, or your benchmark, or whichever point you are using to determine that point so you can use it on your site. So you've done the resection method. There's 3 different resection methods, and the one that you did, whichever one, helps you determine the coordinates of the point you are standing on. So you stand in the position, read different vertical and horizontal readings of different points, and you know their coordinates. So you take those readings, the horizontal readings, and you do your resection to determine the coordinates of where you are standing. Now with the determination of height, you have to take the vertical readings and the heights of those beacons, which are also given to you, and you use that to determine the height of where you are standing. Now, there are 3 methods of determining height in general. There's the barometrical determination of height. That's where you use a barometer, and the barometer is accurate only to about a meter. So this is useful probably more in flight. I know air balloons tend to use this, hot air balloons, but it is only accurate to a meter, and you don't have to have it very accurate. Then you have leveling. So this is rise and fall and height of collimation methods, height of instrument method. This is accurate to millimeters. So this is a very important method when you are using or determining, for example, the heights of a road to determine the slope of the road. So this is probably your most accurate method, but this is only useful when you have a benchmark or a known point on site that is close to you. However, if you have different trigonometrical beacons around you, then this method won't be useful until you determine the point nearby you. And that's why we use a trigonometrical determination of height. Now this is only accurate to approximately 0.1 of a meter, which it can be more accurate, but this depends on how far your beacons are from you, how many beacons you have used to determine the height. So this could give you a fairly accurate result, and this will help you a lot with determining your benchmark for a site that has no close benchmarks near it. So this is the method we're going to discuss today, and this is basically how you make a benchmark or how you determine a point on site. Alright, so the next step, or the first thing you need to know, is understand the concept. So first of all, we have our instrument. Now this instrument is the theodolite. We've taken its horizontal readings, but in this case we're only interested in the vertical readings. Now I'll show you in the next slides, but basically we have what we call the height of instrument. So this is the height from the ground, the point where you are standing, and this is the point height that you are trying to determine to the center of your scope on the instrument, and this is your height of instrument. Then you have your S value, which is your physical distance from your instrument to each of the beacons. Okay. Then what's very important is this is a trigonometrical beacon. It's a concrete pillar with an antenna. Now mostly you try to read that your vertical reading, what we call the middle hair, is on the top of this concrete pillar, and we take that reading. But in some cases this is not possible. Then we read, for example, the top of the antenna. Now when you read the top of the antenna, you have to consider that there's a height of object, HO, from the bottom of the pillar to the top of that antenna. And you need to know this height if you are going to read the top of this. So HO can be 0 in some cases where you are reading the top of the pillar. If you are reading the antenna, then you need to consider this as well, and I'll show you that in the calculation. Then the difference of height is the difference of height from the point you're trying to determine, so the ground where you're trying to determine the height, and the top of your concrete pillar. And then this height you're trying to determine is the elevation, or the height above sea level. Alright, so in practice the following formula is used for correction of curvature and refraction in meters. So this is a value, the k value, which you have to remember. It is 0,7068 s squared. The value of s is the horizontal distance, as I told you, in meters between the known point, which is the trigonometrical station, and the unknown point, which is your height of instrument. Alright, then all of these points, if you want to pause and read through them, this is everything that I explained to you, or most of it is what I explained to you on the sketch. However, you must remember that the height of difference of height is your s tan alpha value plus that k value times your distance squared plus hi minus ho. And that's a very important formula which you have to remember. Then the rest I've explained to you, and then the last thing is your h value. This h value over here is your h minus your delta h if observed from an unknown point. Alright, so if you're observing it from an unknown point, then that is your formula to use. If observed from a known point, then you plus delta h. Alright, then you have alpha is not a vertical angle, not your vertical circle reading, sorry, it is your vertical angle. It can be positive or negative, and I'll show you why. The vertical circle reading of 90 degrees downwards is negative. This influences the indicator of tan alpha. Then the vertical angle can be determined by placing the horizontal hair the theodolite on the desired object height by transiting the telescope and rotating the instrument through 180 degrees. Alright, so I can go through this, but essentially what this is how you determine circle left and circle right. So circle left will be where the bulge part, the circle of the instrument is on your left side. You usually take this as your straightforward reading, and then your circle right is when you rotate the device 180 degrees horizontally and vertically. And these two readings should add up to about 360 degrees. They won't always, but they're going to be very close. Alright, so this is what you learned in practical. For those who have done practical surveying, you'll see the circle left and circle right is what we use to determine our two alpha values. Now why we have two alpha values is if this is where you're looking through the scope and you're looking forward, then 90 degrees is your horizontal plane. If you look upwards, your angle becomes less because straight up is 0 and 90 degrees is in front of you. So picture yourself standing this side looking through your scope, and that's your 90 degrees. So when you look up, the value becomes less. If you look down, the value becomes more. So the difference of angle between this 90 degrees and where you are looking, that alpha value, is 90 minus your vertical reading. With the circle right, you have it that it's flipped around. Now it is 270 degrees for your horizontal looking straight. If you look upwards, the value increases. If you look downwards, the value decreases. And because of this, we need to work out what's the angle, the alpha angle between your 270 and your vertical circle reading. So for circle left, you have 90 degrees minus circle reading or vertical reading, and circle right is your vertical reading minus 270. You'll see these two values will be almost exactly the same or very similar. If they are very similar, you did your readings right. If they're exactly the same, then you read it perfectly. Alright, so now we have to determine with these two, and the reason we do the two is that we can get a better reading because we take those two and we get the average between them, which I'll show you in the table now. Alright, then as I said, the concrete pillar, if you look at the top of the white concrete pillar, the horizontal crosshair is in line with the concrete pillar's top, then HO is 0. If you have antenna and you're looking on top of the antenna, then it is the height of the antenna. Alright, so this is the table that we'll start with. Now please note the black values are the values that were given to you, and the blue values are what we determine. So we have 2 beacons here, and we can have multiple columns of beacons. It's not just going to be 2, but the same rule works for 2, for 3, for 10 of them. Alright, you don't do 10 of them, but 10 of them will technically make it more accurate, or should make it more accurate, let me say it like that. Then these are some of the formulas that you need to remember. For example, the 90 degrees minus circle left. So let me start with, okay, so this is trigonometrical beacon. That's the type of objects there are. Then we have our circle left readings and our circle right readings for these 2 beacons. To get our alpha 1, we say 90 degrees minus circle left. So 90 degrees minus circle left gives us negative 1 degree, 15, and 31. On this side, we have 90 minus 89, 11, 15, and it gives us 0, 48, 45. So this is our 90 degrees minus circle left. For alpha 2, we have the circle right minus 270, as I stated earlier. So now we have this value minus 270 gives us negative 1, 14, 10. See how these two values are quite similar. With this one, we have 270, 49, 0, minus 270 gives us 49 minutes. Now we take these two values of the circle, the alpha 1 and the alpha 2, we add them together, divide by 2, gives us our average. Same on this side. Take the two values, we add them together, and we get the average. Then the distances are given to us. This was either determined from a join and specifically a join from basically our p coordinate we determined in the resection method, or for whatever reason we used the map to determine the distance, but these two distances will be given to you in this calculation. Then this formula doesn't have a name, but it's just part of the equation, so it makes it easier to work this formula out and then use it in the rest of the calculation. Now this formula is the formula we use, that is distance times tan alpha. I can ignore that little dot there, the tan alpha mean. I just put it separate like that so you can see what it is. Now this alpha mean is this value over here, or this one over here for this column. So you take your distance, 3,178, times tan of your alpha mean, and that gives you your value. The same on this side, you take the 5,191.380 times tan of your alpha mean, and this gives you a value. Then for your k values, you have the 0, and there are 7 zeros, 68 times this value squared, and that will give you an answer for your k on both of your columns. Then for height of instrument, this is given to you, so you can just put it in. Because these two are the same, you can probably deduct it as the same setup. So you were standing at one station and you took readings of 2 beacons, so that's why they have the same height of instrument. Then HO, in this case, there's no HO value because it is, you read the top of the white pillars. However, if I told you, or if the scenario told you that you used an antenna, then you have to add the height of the antenna as well. Now your difference of height, as I said earlier, is this formula plus your k value times s squared plus hi minus ho. So you take this, you say, you put all those values in, so you say this value plus this value plus your hi minus your ho, so these four, you add them together and you get this. Then you add these three together minus the ho, and it gives you this value over here. So then the height of beacon given is 1000. Okay, so these were two given values, these are the 2 beacons you read, and those are the actual heights, the elevations above sea level. So what you have to do now is you have to say h calculated, and h is a big H or capital H minus difference of h. So it is this h value minus this delta h. And the reason why it's minus, if I go back quickly, it is because it is from an unknown point. So we minus it because where we are standing is an unknown point. Alright, so we take that value, minus this value, gives us 1779. Same with this one, minus this value gives us that value. Do you see how they are very similar to each other? If you got two totally different values, it's very likely that you did something wrong. So please just double check that. Then the last few steps, just to basically check ourselves and make sure the accuracy is correct. We have to take these two values. Now, if there were 3 or 4 columns, you would have to say all 4 columns or all 3 columns heights. You add them together and you divide them by the number of them. In this case, there's 2. So what I'm doing is I'm working out the average. So please do not always divide by 2. If there are 3 columns, divide by 3. If there are 4 columns, divide by 4. But you have to get the average of all these last values and you get a final height value. Then the last 2 steps, and I'll show you this in the next slide how it fits in your table. You say 1 divided by your distance. So this distance over here, and it gives you this small value. And you do it for both of your columns. So it's this 1 divided by this value and 1 divided by this value. Gives you these 2 values over here. Now what you can do just to make it simpler for yourself is you can make them both, you can times them both by, for example, 1 times 10 to the power of 4, just so you can get them to be 1 value above the decimal separator. Now you don't have to do it like this. It's advised that you do this so you can just make it easier for yourself, but what you do to this one, you have to do to the rest of them. So don't times this by 10 to the power 4 and this times 10 to the power 3, example, etc. What you rather do is you'll say all of them, you say 1, 2, 3, 4 values. So times 10 to the power 4 will get you that 1 to the front of the decimal. And that's why we did it like this. So this is just to make your calculation easier. As long as all of your values stay the same ratio to each other, in the sense of they all times by the same amount. Okay, now what you want to do here is the closer your value is to you, the closer the trigonometrical station is to you, the more accurate that reading will possibly be. So you want to use a ratio where the closer ones, for example this one is closer than this one, has more effect than the ones that are far away from you. It just makes sense, because if you take a reading 10 meters away from you and a reading 100 meters away from you, the 100 meters one is probably not going to be as accurate as the 10 meters one. So that's why we add these values up. So you add all the values up together, you get a total, and then you say the ratio of each one for that total times this height over here, and you get separate heights, so separate portions. If you do the calculation, it'll make sense to you, but basically in this example you say this value plus this value gives you 5.072. Then to determine its sort of fixed height or ratioed height, you say the 3.146 over the total times this height, and it gives you this value. Then you say 1.926 divided by the total times this value, and it gives you another height. If you add these two together, it will get you a new final height. Now if you had 3 columns, then you would have 3 values added. You would say those 3 values divided by the total, and you get 3 different values, and you add up those 3 different values, and it gives you a final height. Now note that this final height is closer, has become closer to this calculated H value than this one. So it's increased in value from here. And the reason why that's a good thing is because that means that it's closer to the one that is close to us and further from the one that is further from us. And that's why we do it like that. Now just for a last slide, I just want to show you this is how you'd write in the value. or your tables values, you write all the values just like this in one table. You don't have to show me all the calculation steps. Just make sure you write everything in like this, and then of course at the end you just write your final height. Alright, so please add your final height. But this is the same steps, please add them like this, and this should help you a lot. Thank you and good luck.